All right, so this is 5.1 part 4. It says, notice that the plus C, which at first may have seemed like a pointless formality, ended up giving us the cost function in its correct fixed cost in example 11. That arbitrary constant can also be interpreted geometrically, so graphically, in the integral of 2x dx equals x squared plus c. The solution x squared plus c is actually a whole collection of curves. So there's one for each value of c. The graph shows below 3 of these curves: x squared plus 2, x squared, and x squared minus 2, with the corresponding c's being 2, 0, and negative 2. So you notice that each curve has the same slope at x equal to 1. We have that same slope of a line. Those are 3 parallel lines at x equal to 1. So it didn't matter what that value of c was. The direction, the slope, which is the derivative, is the same. So in fact, all 3 curves have the same slope at any given x value. And this is because each comes from integrating 2x. So each function has derivative 2x, giving each the same slope. Sorry. This is the geometric meaning of integrating a function. The real result is a collection of parallel curves that all have the same slope, given by that original function at any particular x value. All right, so we've seen that differentiation is kind of breaking down or changing total cost into marginal cost. Integration is the reverse process, therefore a kind of adding up and recovering the total from its parts. We're doing that inverse operation. So for example, ordinary addition is for summing chunks, such as $2 plus $3 equals $5. Whereas integration is for summing continuous change, such as the slow but steady growth of an economy over time. So in other words, integration is a continuous summation. And as for the uses of integration, it's going to recover cost, revenue, and profit from their marginals. And in general, it's going to recover any quantity from its rate of change, together with a particular value. And remember that particular value is going to give you that c, that arbitrary constant. The inverse relationship between integration and differentiation is shown below in the following diagram. We've got revenue, cost, and profit is the marginals. So if we take the integrals of the marginals, we get revenue, cost, or profit. The integral of the slope gives us the curve. The integral of velocity would give us distance. And the integral of any rate of change would give us any quantity. Okay? And vice versa, if you take the derivative of any of these, you're going to end up with the other side. Okay? So it's a continuous loop that works either way. All right, that's the end of our first step into integration.